Guys, good morning. Today we're going to be talking about circles. We're going to be introducing circles to you guys, some of the definitions that go along with it, and a couple of ideas that we can use on circles to kind of broaden our horizons with circles. So, starting off, definitions. First off, we have circle O. So, the way that we're going to denote these is we have a circle with a point in the middle, and that means circle, and then we name the center of our circle. In this case, it's O. So we have circle O, that means that O is the center of the circle. Next definition that we have is concentric circles. What that means is that those two circles have the same center. So I have two circles here. They both share the same center. So they're concentric circles if they share the same center. And it will kind of look like a bullseye whenever you see these types of circles. Next up, exterior. That just means outside the circle. We can see that down below with point Q. Interior means inside the circle. We can see that with point P. That's inside the circle. It's not on it. Very important that it's outside, inside, but not on. And then point N is on the circle, as we can see right up here. So those are some simple definitions for us to get started. Let's continue it on. Now, the ratio of a circle's circumference to its diameter is pi. So the way that we found out the circumference of a circle, we know that circumference is equal to diameter times pi. If I want to solve for what the ratio of a circle's circumference, of course we know ratio means division, to its diameter is, I just divide both sides by diameter, as we can see right over here, and we get pi is equal to circumference over diameter. So pi is the ratio of a circle's circumference to its diameter. Next, we're still on the topic of circles. So what transformations make sense with circles? So the first one that we have here is a rotation. Well, if I rotate a circle around its center, point P, would it do anything? Well, no, the circle would just rotate a little bit, but it would not change anything about this shape. It'd be the same exact shape that we started with. So nothing changes with rotation. So that transformation doesn't really make sense unless you're going around a point that is not the center of the circle, at which point the circle would just rotate to a different spot on the coordinate plane. Next, a reflection. Would a reflection of circle T across the y-axis change anything? Well, yes. It just changed the position of circle T. So just reflect over it, and then we'd have circle T prime on the other side. So yes. Next, a translation. Well, with a translation, what are we doing? Well, we're just moving it from one point to another across the vector. So would translating circle Q along the vector 1, -3 change anything? Well, yes, it changed its position on the coordinate plane once again. So I'd move my center 1 to the right, because it's +1, and then down 3. And we'd suddenly have Q prime, circle Q prime right down below at a new position. And then lastly, dilations. Well, what would happen if I were to dilate a circle? Would a dilation at the origin change the circle R? Well, if we think about this, yes, it would change it. It would either make it larger or smaller based upon our scale factor. So, assume that this is the same circle, only drawn a little bit better. We can see that it would be the same exact circle, except it'd be larger or smaller than the one in the center that we dilated from. So yes, if the scale factor is bigger than 1, enlargement, if less than 1, a reduction. So, all circles are dilations of one another. Is this true or false? Well, it'd be true. No matter what, I can change these circles and dilate them to become one another. It's the same all the way through with any type of circle. So all circles are dilations of one another. That's absolutely true. Would that mean that all circles are similar? Yes. If objects are just dilations of one another, that means that they're going to share all the same angles, all the same properties, so they are similar to each other. All circles are dilations, so all circles are similar. All right, some more definitions. These are the definitions that you guys will be seeing in the problems. So the first one that we have is chord. A chord is a segment with endpoints on the circle. So right here I see that we have the segment here, segment AB. I'm starting at A, stopping at B. And both endpoints lie on the circle, so therefore line segment AB is a chord of this circle. The next one that we have is secant. So secant is a line, ray, or segment that passes through a circle. So we said segment AB was a chord because it has both endpoints on the circle. Line AB is a secant because it passes through the circle. It continues going on. So if it continues going through, it's a secant. If it stops at the end of the segment, then it's just a chord. Next, tangent, very important one that you guys should know. Tangent will be playing a key role in calculus for you guys down the road. It's also just very good for us to know this trigonomic property, trigonomic function. A tangent is a line, ray, or segment curve that touches a circle at one point. So, as we can see here, this purple line, it touches our circle just at one point and then continues on. Tangents will only touch at one point. They will not touch again. If they touch again, it won't be a tangent at all. It'd be a chord, because it'd have 2 points on there. Lastly, point of tangency. Well, that's the point where the tangent touches the circle. So in this case, point C is our point of tangency. So just some definitions for us to know. I'm going to be asking about these later on while we're going through them. So make sure that you know how to identify a chord, how to identify a secant, and how to identify a tangent. Knowing all three of those will be very important for you going forward. All right, properties of chords. So here's our first property. The distance from the center. The length of the segment from the center to the midpoint of the chord, so that's from O to the midpoint of XY, that will always be going from the length of the segment from the center to the midpoint of the curve. So we can actually see that when we draw this, it creates two congruent triangles here. So we have these two segments being congruent because it's the midpoint, and then we also see that it turns perpendicular right in here. And that's very important for us because at that point, once we see perpendicular, we can automatically go to Pythagorean's theorem to solve, or we can use anything like that to kind of solve for the radius, for the chord length, or even just for the distance from the center to the chord itself. So we'll be able to do all that. Now a radius that bisects the chord is also perpendicular bisector of that chord. So if I have my radius here, this blue radius, and it intersects our chord, passes through that chord, that radius is also a perpendicular bisector of the chord. So it's cutting it in half, and it's meeting at a right angle. So it's the same exact thing as we see right up here, only up top we don't actually see that's the radius because we don't continue it on, but that is indeed a radius if we needed it to be. All right, so let's go ahead and try this out. Hint, make right triangles, connect the radii. You see that circle X has a radius of 15. We want to find the distance from X to CD. So I'm going to go ahead and draw my radius here. My radius is 15. And I know from that last slide that if my radius cuts this chord, it's cutting it perfectly in half at the midpoint and giving me 12 on each side because the whole thing's 24. From here, I'm going to go ahead and draw those triangles that they're saying that we should draw in. And I now have a right triangle. So from here, we can go ahead and solve for this thing. So I see that we have 15 for my radius, right? I can do X to D would be the same length as our radius because radius is the same all the way through the circle. So I have 15 here. I want to know what X is. I want to know the length from from our center, X, to chord CD. So I'm looking for this length here, this X. So I now have 12 squared plus X squared equals 15 squared. That'll give us 144 plus X squared equals 225. X squared equals 81. Therefore, X is equal to 9. So there we have it. The length of the segment from the center of the circle to chord CD is 9 in length. And again, as long as you remember that the radius is the same no matter where you're at on the circle, That makes these a lot easier. All right, next up, properties of a tangent. A radius drawn to the point of tangency, so if I draw this radius here from the center to the point of tangency, that will be perpendicular to the tangent line. So our radius and our tangent line will always be perpendicular at the point of tangency. It's very useful for us to know that. It's always going to intersect at 90 degrees. Very important for us to know going into calculus as well. If two tangent segments are drawn to a circle from an external point, then those two segments are congruent. So, as we can see, I have this single point out here, point C, and if it's tangent on both sides, point A is a point of tangency as well as point B, then these two segments, AC and BC, are congruent to each other. That's all it's stating. All right, let's go ahead and figure this one out. First, name the following. So, line of centers. Well, we have this line here going from the center of a circle to the center of a circle. So segment PQ would actually be our line of centers. Common internal tangent. Well, if it's internal, that means that's inside. So it's going to be in between these two circles. So XY is our common internal tangent. It's common because it's shared by both, point X and point Y. And it's a tangent line on both of them going in between. So that's why it's internal, because it's in between them. Common external tangent. Well, A and B are both points of tangency. As you can see, line AB does not go in between them. It's on the outside, so it's external. So it's common because they both share those points. It's external because it doesn't go in between them. It goes on the outside. And then it's tangent because it only touches at one point. So AB, line AB is our common external tangent. All right, a little bit more difficult of problems. Common tangents. So we have these steps here. Our first step is to join the centers. So if I see here, I have point Q and point P. I'm just going to join those centers. And I know that this would be length 8 because the radius doesn't change, because this is 8. And for Q to our other circle, that'd be 18, because we can see our radius is 18 up here as well. So the whole thing, 8 plus 18, will give us 26 as our full length. All right, so from there, through the smaller of the circle, draw a line parallel to the common tangent until it hits the radius of the larger circle, making a rectangle and a right triangle. So I'm going to go ahead and make a line that's parallel to line segment AB, but it's going to start at P. So I'm just going to go ahead and draw a line parallel. There it is. Now I know that at point B we have a 90-degree angle, same with point A. I know that because those are points of tangency. The points of tangency always intersect at 90 degrees, which means that this creates a nice right triangle for us, as well as a nice rectangle. So from here, use the Pythagorean theorem. So draw the centers. All right, so we're going to go ahead and use the Pythagorean theorem here to solve for the length from point P all the way over. Now, the reason that I know that this is 8 is because it creates a rectangle. So if this is 8, opposite sides must be congruent, this must be 8. The whole thing is 18, so this tinier segment here must be 10. So from here I can use Pythagorean's theorem of 10 squared plus x squared equals 18 squared, as we can see right up here. Or sorry, not 18 squared, equals 26 squared. That'll give us x squared plus 100 equals 676. Subtracting 100 from both sides, we get x squared equals 576. We take the square root, we get x equals 26. So we found out that x is 26 right here. But we're trying to find out a to b, which is also x. And they should be the same distance since it is a rectangle. So a to b should be 26 units overall. All right, the last problem that we have, this one's a little bit more difficult than normal, but let's go ahead and try it out. So, the walk-around problem. It says, hint, label the side or piece of the side you're looking for as x, and start walking around the problem. So, to get started, we know A to B is 10. We know B to C is 15. We know A to D is 18. And we want to find the length of CD. That's our goal. What is the length of CD? So, to get started on this, I'm going to go ahead and first call this section, because I know that our whole thing is 10 here. I'm going to call this section from the point of tangent C to B. I'm just going to call that X. So therefore, this section down below, if the whole thing is 10, just from here to here should be 10 minus X. The whole thing's 10. I'm taking out this section of X. From there, you can also say that this is the same because, again, it's a common endpoint, and they're meeting at points of tangency, so this would be 10 minus X, this would be 10 minus X. From here, and here's the part that we need to think, this little section is what we're looking for, this green section. So the whole thing is 18. I'm subtracting the red part, 10 minus X. So 10 minus X. Now from here, I have this negative out front. I need to distribute that through the parentheses. If I don't distribute it, it's going to cause a mistake. And we get 18 minus 10 plus X. So this section is actually 8 plus X. So the green is 8 plus X. Now that I have this section, I still need to find out what C to that point of tangency is. So I'm going to go ahead and go back to this 15 and this X over here, and I'm going to use that information. So if I know this part is X and the whole thing is 15, this section should be the whole thing, 15 minus X. Which means that this other section should be the same thing, 15 minus X. Now lastly, if we want this whole length from C to D, we can say CD is equal to 15 minus X plus 8 plus X. If we look at this, our X's cancel out. 15 plus 8 will give us 23 units. And that's it. The homework is available on Schoology. I will have another video posted for the next section. Go ahead and try this out. It is due Sunday. If you need anything else, please let me know. Other than that, thank you guys for watching. Take care.